Good morning, everyone, and welcome to this presentation, which is about managed code rootkits. My name is Erez Metula. I'm the founder of AppSec, an application security dedicated company based in Israel. And what I'm going to talk about today, I'm going to talk about application-level rootkit attacks on managed code environments, which is something which is kind of scary. What we're going to talk about today, we're going to start with an overview of application-level runtimes, application-level virtual machines. We're going to see what is an MCR, a managed code rootkit, that hides itself inside the managed code environments. We're going to see how managed code rootkits changes the definition of a programming language. Think about it. Changing the definition of a programming language means that code that the developer writes actually does something else than what it was intended to do. And we're going to have a couple of case studies of virtual machines environments. We're going to see an examples of .NET. We're going to see an example of Java JVM. And we're going to see an example of the Android Dalvik virtual machine. So that just to demonstrate that the concept is relevant to all of the application level runtimes. And we're going to see some very interesting attack vectors and examples. And we'll also see the tool that I've developed called Reframeworker that allows you to change the runtime on which the application runs. We're going to see a couple of examples of how useful it can be. A little bit of a background. So I started thinking about the idea of changing the runtime, changing application level virtual machines back in late 2008. I wrote a white paper called .NET Framework Rootkits. When I first presented this paper, people thought that there was some problem with Microsoft.NET, with the .NET framework. People started bashing Microsoft about these kind of things. So I decided to show that this concept is relevant to other platforms as well. So I extended this concept, and I extended it to other languages that I talked about before. And I presented this material in Black Hat and in CancerQuest and in RSA OSP and all kind of other places. But for me, it was very important that each time that I present this idea, I change it and I add it a little bit more. So if you had a chance to see this presentation, something else, be sure that you will see here today some new stuff. A book about this subject is coming soon. I'm publishing with Singers the book called Managed Code Rootkits. It's about to be out in about 2 months from now. And it covers what we're going to see today, which is very dense. Today we're going to see just 1 hour of this subject. So if you want to have more information about it, be sure to look for it. So managed code rootkits, those are the kind of runtimes in which the code runs under the management of an application level virtual machine. We're talking about environments in which the code that is inside the executable does not contain machine-level instructions, such as those in languages such as C and C++, in which the source code is compiled to the machine-specific instructions. But we're talking about languages in which the code is compiled to an intermediate language bytecodes, so that when we have this kind of executable, it runs inside the virtual machine. On the right side, we can see this virtual machine. So we can see that on the bottom, we see the hardware level, operating system level, and we have basically two kinds of executables. On the left side, we see the unmanaged code executables, such as C, C++, and stuff like that. And on the right side, we see that the managed code executable runs on top of the virtual machine. By the way, do not confuse with OS level virtual machines, such as VMware, and such as virtual PC, right? So we're talking about application level virtual machines. Well, the idea of the virtual machine allows us to write the executable once and run it everywhere. The application virtual machine performs the translation for the machine-specific instruction set at runtime. When we're talking about application level virtual machine executor model, we have the source code, which is compiled to the bytecode, to the intermediate language, which is a kind of abstract level assembly code. it's very similar to assembly code that you are familiar with, but it has the notation of objects, of inheritance, basically everything that relates to higher level code. And when the code is loaded inside the virtual machine, it is first loaded by the loader. The loader takes from the runtime some kind of information, such as those contained in the libraries, which can be a DLL in case of .NET, a jar in case of Java, even in Dalvik, and basically every language has its own runtime classes. And in runtime, a mechanism called the JIT, just-in-time compiler, converts one line of virtual code to machine-specific code. It can be a couple of lines, so that we have an engine that always gets inside a virtual machine language and puts out some kind of assembly instructions specific to this environment. So when we're talking about managed code rootkits, we're talking about changing the internal definition of the runtime itself, so that we can actually change the language instructions, we can change the language methods. By the way, method in object-oriented language is what you all used to call the function, right? So we're changing the methods, we're changing the default values, event handlers, so we're actually changing the runtime itself, and this allows us to change the flow of the execution, of the executable, sorry. So we're basically creating an alternate reality for applications. So application thinks that they're executing something, but they're basically executing something completely else. So we are kind of changing the matrix in which the application is deployed on. And the interesting thing about an MCR is that due to the fact that it runs from within the virtual machine, it actually has a root-like access to the runtime itself. It has access to private methods. It has access to operations that are not allowed by the application. So it basically changed the whole idea of managed execution. So if we take an example of how it can be done, well, it can be done in a couple of ways. It can be done by changing the libraries. It can be done by hooking into the JIT. It can be done by maybe hooking into some other mechanisms. But for the purpose of demonstration, we'll do that by changing the runtime libraries. So if we have the three layers, we have the application layer on the top, we have the virtual machine layer at the middle, and the operating system at the bottom. When there is some kind of code that calls a runtime level method, which is kind of compared to system call, the operating system, well, the runtime contains its own implementation of the code. What we're going to do is we're going to take this function, throw it away, so we have our own implementation, so that when the code calls this kind of method, it will do something completely different. And of course, when the call will come, the system will be hacked, right? So let's start with a simple demonstration. In this demonstration, we're going to change the Java language. This will be the basic of Java rootkits. So our next demonstration will be that, we're going to take the method that prints string, the print line string, right? We're going to take the hello world executable. So we're going to see how if we take the print line method and double its own implementation, we'll have the same string printed twice. So this will be just a proof of concept of language modification, but it will allow us to do something more advanced later on. So first thing that I'm going to do, well, I'm going to take and I'm going to hook into the Java rt.jar. rt.jar is the Java runtime classes. So basically a jar file, as you probably know, is basically a zip file, right? So if I take this the jar file, it is actually deployed inside the Java runtime. So if you go to the runtime, you will find it there. So I'm just changing it to zip, so I'll be able to get inside. So this is basically just a zip. And I'm going to the class that implements the file IO. File IO is being in Java IO, and over here I have it a file and I have it a buffer. So I'm going to take the file outside. And after I've copied it outside, I have here now the class itself. But the class itself doesn't contain anything meaningful. It contains the Java bytecode. What I want to do is I want to disassemble it. So, by the way, guys, we have a small class, so feel free to raise your hand and ask questions. This is what's so great about Boston Conference, right? Source Conference. So, Is everything okay up until now? Great. So the bytecode itself cannot be, I cannot tamper with it. I cannot decompile it. I need to disassemble it. I cannot decompile it because if I need to do some kind of a round trip, I need to go back to some kind of thing that I can manipulate and go backwards. So what I'm going to do, I'm going to disassemble it, and this is what I got. So this is the output of disassembling the class itself. Later on, I'll show you what are the commands that I used. The interesting thing is that I have to use a disassembler and an associated assembler. There are tools that know how to disassemble and there are tools that know how to assemble. But they don't, you cannot usually take the output of one of them and put it to the other tool. You must have a tool that comes with an assembler and disassembler as a pair. So let's go to the implementation of the method itself. This is the method that implements the print line. So this is how the bytecode look like. This is the disassembly of the bytecode. This is the code itself. As you might see, it resembles assembly code, right? And the idea is that when I looked at this method, when I started to experiment with this idea, well, I look at the implementation of this method, and I realized that the code that does the actual printing is this kind of code. So just for the purpose of the demonstration, to see that I was going at the right direction, I took this piece of code and double it. So you can see it on the lower level, the lower part, you can see the same code over here. So I saved the file, assembled it back to the class, pushed it back into the jar, and deployed it back into the runtime. So if I'm going to take this code, so I'm going to execute the Java, the hello world class. So I'm going to run the hello world. And this is what happens if I'm executing without deploying the file, right? So I'm going to deploy now the file itself. So I'm going to overwrite the jar file to the specific location. So if I'm running the same executable now, I'm getting 2 prints. So this is the basic idea of modifying the runtime. We're going to use it to deploy rootkits into the runtime. Of course, you can take it to any direction that you want. Guys, is everything okay up until now? Great. So the basic steps that I did is that I took the runtime and I used the disassembler and assembler pair is the tools that called Jasmine and Jasper. Jasmine, Jasper are the assembler, disassembler key associates, so you can use to do it in order to deploy it. Back here you have all of the steps, so you have it for, you can have it for reference, you can use it later on. This is the basic steps that I did. So the interesting thing about an MCR is that it targets the applications rather than the OS. We are used to rootkits that target the kernel that targets hardware. Now we're talking about rootkits that target applications. And so we're going at, so if we're talking about deployment of this kind of rootkits, well, deployment of MCR usually requires an admin level permissions. But again, this is not something that bothers us so much because this is an application level attack. So we are assuming, just in other kinds of rootkits, we are assuming that the previous compromise of the machine has already been taken by the attacker. So we're talking about the common attack vectors like in other kinds of rootkits. One kind of attack vector is housekeeping. The attacker has already got to the machine, so he's exploiting some kind of vulnerability. So now he has full control of the machine, but he wants to keep controlling it. So we need a housekeeping attack vector. And MCR can be that kind of attack vector. A second attack vector is trusted insiders. Trusted insiders are those guys that already have access to the machines. We're talking about developers. We're talking about DBAs. We're talking about system administrators. Those are the guys that are sitting in an organization and they already have access to the machines. So, and maybe some kind, maybe they want to deploy some kind of attack to the organization. And the third attack vector, this is when some kind of malware deployed another kind of malware. That other kind of malware can be an MCR. So think, yeah.
Wouldn't path traversal against the application itself be a useful attack, which then wouldn't necessarily require, the admin level privileges, or does the typical deployment of the JVM prevent those kinds of traversal attacks, such that could cause you to overwrite a jar file or something?
Well, it all depends on the ACL that was defined for the runtime. Usually, it is the runtime are deployed using an administrator privileges. But let's say that someone deployed the runtime using a regular user. Oops, sorry. So you don't have to use an administrator for that. So, for example, like you said, if you have some kind of a web application, let's say, in which the runtime is using a regular user, and you're able to overwrite the code, you do not have to use an administrator level privileges. Okay. There are many kinds of payload that an MCI can deploy. It can provide stealth operations. It can execute commands. Basically, everything that other kinds of rootkits can do. And when we're talking about an MCR, the interesting thing is that the MCR lies to the application that's running on top of the runtime. So it can maneuver the applications. It can provide stealth for the own operation. So that even if an application will try to detect a compromised runtime, well, think about it, the runtime will lie. So the application will say, hey, are you compromised? And the virtual machine will say, yeah, I'm okay. And sorry, I'm okay, everything is fine, nothing happened. This is because we can manipulate the answers, right? And since we can report false information, we can report false information about files, about processes, about registry keys, basically about anything. And let's see an example of that. And in this example, we're going to hide a specific file. The file we're going to hide, the implementation of this kind of attack will be on the machine of the virtual machine specific method that returns a list of files to the upper level applications, so that all of the applications are using the same method to get the list of files, right? So by deploying it once, we can actually manipulate all of the applications. Well, this kind of method, in .NET it's called get files, in Java and Dalvik, Android it's called list files. So we're going to hide the file called secret file. By that we're going to change the runtime and deploy it. And for the next demo, we're going to see the Dalvik runtime. We're going to see the Android Dalvik runtime. And for that, I'm using a virtual machine called Live Android. Live Android is a virtual machine, a live CD for Android. You can play with that. You can see, it's very interesting to look at this virtual machine. So, if I'm looking at some kind of file manager, I took two examples. I downloaded the two file managers from the net. It can be any file manager, just to show you that when I deploy it once, it influences all of the file managers. So one of them, the OI file manager, it allows me to look at files that can go to directories and see the content of the directories. So what I'm going to do, I'm going to deploy the file that I've created. What I did is I took the implementation of the file itself. I took the file that called core.jar. Core.jar is the file that implements the core functionality of the Android virtual machine. And inside of it there is the file class. I decompile it and I got this kind of code. This is the intermediate level bytecode, disassembled code of the file. So I'm going to find the list files, and this is the implementation of the list files, and this is the code that I've injected. I've injected a code that says, well, put the string secret file to a specific register called v1. By the way, I didn't say it, but what's special about Dalvik is that Dalvik is register-based rather than stack-based execution model, so everything is passing around using registers. Okay? So I'm putting the value that I want to hide secret file, and I'm invoking a method called hide file. Well, where did hide file get it from the first place? Does Dalvik provide a method called hide file? What do you think? Where did hide file got from the beginning? I added it. So I also be able to inject methods, right? So I injected a new method. I created a method called hide file. You can see it here. This is the code of hide file. Okay? So now I've actually extended the runtime. I'm providing a method in which I can use. So it allows me, you know, like any good software developer, instead of having one big chunk of code, I'm compartmentalizing a little bit. So it allows me to do parameter passing and basically to write better code. So now all I have to do is provide it with the parameter that I want to call. And this is the implementation of the method itself. So actually, when I call this file, right, when I deploy it, and if we look at the virtual machine itself, let's go to the sorry. Yep. This is the shell for the Google Android. So this is the basic command line, and now what I'm going to do, I'm going to go to system. Well, system contains all of the important information about the runtime, and I'm going to framework. Framework is where the runtime of the Google Android runtime contains the Dalvik classes. So this is where all the interesting thing happens. So back here you can see the two files, the core and the core _patched. And what I'm going to do, I'm going to copy this patched file over the original one. So now overriding the file itself, and I'm going to go back to the system file. And And what I'm going to do now, I'm going to create a couple of files. So I'm going to create, let's say, file that's inside SD card and called 1.txt, another file called 2.txt, and the third one called secret file.txt. Okay, so got back to the runtime itself. Go to my file manager, and if I'm looking at the SD card, I see only the two files that the runtime is supposed to see. Of course, if I will create another file, 3.txt and 4.txt, well, I will see only those that I want the runtime to see. So we actually created this alternate reality. So if this is the real world, right? This is what happens inside the matrix. So now it allows me to do interesting things. I can hide processes. Okay, I can hide processes. I can hide everything that I want. I can influence the execution itself. Yeah.
So the basic assumption is that those jar files are not signed or anything. So like if those are modified.
This is a good question. Well, let's say that they were signed, right? They're not signed. But let's say that they were signed. Well, if I'm an attacker and the machine has already been compromised, nothing can stop me. So even if it was compromised, think about it. Even if it was compromised, if it was signed, there must be some kind of a private key lying around somewhere, and an associated public key to perform the signing and the verification. Well, I can just replace them and re-sign again. So actually, if you have a full control of the machine, you cannot do anything about it. This is exactly the definition of rootkit, because you cannot fight something which is on the same level as you are.
So on timing of this, when you replaced core.jar on Dalvik, you didn't have to restart the again.
No.
You didn't have to restart the
No.
runtime. So
No.
the class loader is picking up the changes
Yeah.
as you make them?
Yeah. Well, what I do have to do sometimes, well, in this situation I didn't have to do it, is to clean precompiled images. So, for example, if I want to go back to the real world, right? So, for example, I'm going to copy the original, I think it's over here, core, oh, it's in backup. And over to here, right? Basically, I want to remove all of the pre-compiled images. Pre-compiled images is an images that was already compiled to the specific machine, so that the JIT, remember the JIT, doesn't have to go and compile again and again. So it saves the machine-specific instructions. So I have to remove it from. This is in data, Dalvik. So this is the Dalvik cache, and remove everything. So if I want to go back, for example. This is if I want to do a real cleanup, right? So if I go and do it again, and go to my SD card, now I can see the file, right? So this is the actual change this is what happens if it wasn't modified. Okay, so the basic steps that I did is written over here. You can have it for reference. Of course, the slides will be here. It's online. You can download them and do everything you want with that. So I showed you that we can do method injection. We can actually add new methods and new classes. Basically, we can extend the runtime so that it will allow us to do something that wasn't intended at the first place. And I implemented a couple of examples. One of them is hide file that you saw, hide processes, send to URL, we send information to external URL, and basically other interesting things. Another interesting thing about injection for virtual machine runtimes is that they're object-oriented based. Object-oriented means that when I'm injecting to a specific class, basically I'm injecting to all of the classes that inherits from it. In object-oriented models, all of the methods, we do not have a shallow execution model, so that every method, every class inherits from another class. And all of the classes in this hierarchy, all of the classes inject from object. So for example, if I'm injecting code to object, well, I'm actually injecting to all of the classes, right? This is kind of interesting because it allows me to decide where I want to inject. For example, if I want to inject just to one branch, just to this area, I will inject to this class and everything inherits it automatically. Another example is with authentication backdoors. Think about it, what happens if someone manipulates the authentication method for the runtime so that application calls the authenticate method. It will lie to the applications, right? So that, for example, if you want to inject something that says, if the password equals some kind of magic value, let the user in. So this is a kind of master key that lets you enter inside each and every one of the users. You can just inject it to the authenticate method. This is an example of a .NET rootkit on the authenticate method. Another interesting thing is what happens. It's something that I call the false sense of security. Do you see this picture on the right? This is a real picture. Someone actually bought a lock. And this is how he locked his bicycle. False sense of security is one of the bad things that can happen to security because you're thinking that you're okay, but you're not. You're thinking you did the right thing, but you're not. So basically, someone can hack your system. And one of the interesting things is what happens with false sense of security regarding to crypto attacks. Well, think about it. What happens if someone tampers with the crypto libraries and changes the method that is responsible for generating random keys for encryption? So if this is the real code, let's say that we replaced it, so now we have this code. So that now the random number generator returns a fixated key so that the application developer thinks that he's encrypted the data. Well, he encrypted the data, right? Only that the data, the attacker knows the key, he controls the key. And the output looks encrypted. Well, it is encrypted. Another example is what happens if someone sends the key to some remote location. And another example, this is called algorithm downgrading. This is what happens when you're calling some kind of a crypto algorithm, which is considered good, but the algorithm is being downgraded to a bad algorithm. For example, if we take AES, the advanced encryption standard, and replace it with DES, so that the application calls AES, at the bottom level, the actual encryption is being done with AES, so that the other guy will be able to crack it very easily. Another example is when we're changing the modes, going from CBC to ECB, right? Going to CBC from ECB means that from doing good encryption, we're doing crappy encryption. And just to show you how ECB mode over good encryption, such as ECB, if this is the over AES, if this is the original image that we want to encrypt, this is how it looks like when it is encrypted in AES using ECB. So ECB is bad. Well, there are a couple of examples: sending the information to a remote attacker, for example, sending the passwords, sending the data, sending a connection string. We can manipulate with the DNS. There are a couple of examples that we can do. Go and read the paper, and if we want to rate for the book, so you can have a more detailed information on that. But basically, those are the examples of what you can do. Well, the .NET CLR, it actually contains a signature. If now we're talking about .NET Rootkits, and this is related to what you asked, .NET actually contains a signature. And in .NET, the runtime is installed inside the GAC. GAC is the Global Assembly Cache. And in the GAC, every assembly has its own signature. So if I'm going to the GAC on the machine that we're going to attack, this one, for example, and I'm going to see Windows, Assembly, GAC. Okay, if I'm going from the beginning, Windows, Assembly. Here I have a couple of versions of the GAC. So let's go to GAC 32. Let's go to, for example, MS-core-lib. MS-core-lib contains the basic class libraries. Now we have the DLL itself, only that its signature is based on the directory name. So you can see it over here, that I'm talking about MS-core-lib version 2 _ B77 something. This is the signature. So the .NET Runtime actually checks signatures, but it checks it upon the name of the directory. So I can take the runtime, take the DLL, and put it on the correct location, and it will be replaced. And from the framework point of view, everything is okay. But again, this is not a problem specific with the DLL. This is how it was implemented, right? So this is the basic steps for the .NET Runtime. Again, it is here for reference. You can use it later on. An important thing about the DLL, the deployment of rootkits into the .NET CLR is that you have to disable Engine. Engine is the machine-specific precompiled image mechanism, so that even if you replace the DLL but you do not engine it back, it will still use the precompiled image, right? Go read the paper, it will explain it a bit more, but this is, don't forget to do it. Well, when I did the experiments of managed code rootkits and basically runtime manipulation, it took lots of time, and I decided that I must have a tool that allows me to perform automatically language modifications, and I didn't find any tool, so I decided to write one, and I wrote the tool called ReframeWorker. For those of you that heard of it, the previous name of ReframeWorker was .NETsploit. Since then, I extended it to support other platforms, not just other frameworks, not just .NET, so that it is actually a generic language manipulation platform. You can actually take a runtime and write rules of how you want to manipulate the runtime so that you can inject code into it, change the behavior, and do some very interesting things. And the idea is that it provides you with all the necessary information. It can even generate easy-to-use deployers, so that all you have to do is take the output of it and deploy it on the target machine. It is easy extendable. You can, basically it's open source, so you can do everything you want with it. It comes with many modules, and you can extend them, you can add modules, you can share modules. So it is actually a platform. And the ReframeWorker module concept is based on the idea that instead of having one piece of code, let's divide the operation to a couple of generic pieces of code. This is the building blocks in which an injection is being performed. So we have a separate code for payload, we have a separate code for method, for classes, for references, and we have an item. An item is an XML that defines an actual injection. An item is the basic set of rules that says what should be injected and where. And this is how an item looks like. And this is, although a simplified item, this is an item that says, I want to inject a reverse shell into a method called run. And it actually contains all of the information needed. So we have here the name of the target binary, for example, msclib. We have here the location of the binary. This is where it is located on the GAC. We have here the payload attributes that defines what is the injected code that will be injected, and of course, where is the hooking point, where we want to inject the code. We don't want to inject it anywhere, we want to inject it in a specific location. So, if we're going to look at framework here, well, framework here comes with with many modules. The modules itself are saved in the directory called modules. Here you have the separation of all of the code. So, for example, if we're going to see now an example of an injection of a reverse shell. And if this is the item of reverse shell, this is all of the information needed for the tool to know where to inject the code. We can see that it is combined from a payload called conditional reverse shell form.payload. It is combined from one method and one class. The class, by the way, is netcat. We're going to implement the reverse shell using netcat. But again, this is just a way of implementing it. So if I'll run a framework here, this is the UI of framework. I'm going to load some kind of item. You can see here that there are many items that are defined that you can use. This is for many of the attacks that I described, for the backdoors, for the encryption keys, for hiding process and many of the other stuff. And I'm going to load the conditional reverse shell. By the way, it is conditional because I want a reverse shell to open to the target machine only upon a specific execution of some kind of executable. I want the reverse shell. By the way, you all know what is reverse shell, right? A reverse shell, so for those of you who doesn't know, a reverse shell, it is something that looks something like this, that says, well, I cannot connect to the machine, to the affected machine, but I can instruct the affected machine to connect back to me. This is usually in a scenario in which you have a firewall that blocks incoming connection, but does not block outgoing connections. Okay? So, what we're going to do now is we're going to start the injection itself. So I clicked on start after loading the conditional reverse shell, and I can see here in the, that there are three modules that are going to inject, right? One payload, one method, and one class. Over here we see the progress. We see that it is being disassembled, and we see the payload was injected, and the method was injected, and the class was injected. And after that, we'll see that it will reassemble back a new DLL. And if everything works as expected, it will say that everything is fine and you have a new DLL, and it will ask me if I want to generate deployers. So a couple of minutes, seconds later on, that's what I was waiting for, I see that it says me that everything is fine. And it asks me if I want to generate deployers. Remember, deployers are those batch files that allow me to inject the modified code. This is deploy.bat, for example. And if I want to go back to the original behavior, I need another batch file. This is the undeployed batch file, right? So it allows me to go back and forth and to test some kind of code, go back and do some other things. So I injected the code, and let's set the stage. So if this is the affected machine, right? Let's add the attacker. The attacker on the right, this machine, a separate machine, is running netcat in listen mode on port 1234, right? So our target will be to execute, let's close this one. Our target will be to execute a file called sensitive application.exe. So this application is the application that when it is executed, I want the reverse shell to be issued. So think about some kind of application in which there is some logic to open a reverse shell, for example, VPN or stuff like that. But nothing happened, right? This is because I didn't deploy the DLL yet, the MCR yet. So I'm going to deploy it. By the way, this is the deploy file. This is how it looks like. It generates everything needed in order to do the injection. So let's run it again. I'm running the same executable, but now the code that was injected into the runtime says if the name of the application equals sensitive application.exe, open a reverse shell to the other side, right? So if everything works as expected, when I will execute this one, we'll see that the reverse shell will be opened on the right side. And let's see if everything is okay. And yeah, I have a reverse shell. Right? So let's see that it is okay. Let's do an ipconfig. And I see that I'm over at the other side. Who am I? Well, I'm an administrator. Great, everything works as expected. Of course, I can close this one, and well, the reverse shell will still be open, right? So this is an example of a reverse shell which is injected into the runtime itself. So there are a couple of bad news, right? The bad news is that we have another attack vector to worry about. The runtime itself can be modified. And the problem is that there is very poor awareness regarding this issue. Very few people check the runtime. People trust the runtime too much. And we're talking about that code reviews, they do not check the runtimes. Code reviews, and I know because I do lots of code reviews, and most of the code reviews are being performed only at the application level, but no one checks the runtime itself. And of course, and again, forensics, they also do not check runtimes. So the bad code can be hidden over there. And the interesting thing about this this code is that, well, an MCR is cross-platform by definition. This is not like a payload that the malware developer has to write for Windows 32, 64, to Linux and to mobiles. He writes it once, and the virtual machine performs the conversion for him. So the same class can be deployed many times, right? Another interesting thing about it is that it is not relevant. It is relevant now for applications, but as time goes by, operating systems are started to be built on managed code environments. And if we look at the example from Microsoft, Microsoft has the Singularity project and the Midori OS that will be out sometimes, which is an operating system implemented solely with managed code runtime virtual machines. And the interesting thing is that an MCR inside the managed code OS is equivalent to a kernel level rootkit of today's operating system. Okay? Another bad thing is that MCR allows the attacker to do object-oriented malware. This is the name that I gave it to describe something that takes advantage of object-oriented, of inheritance, of polymorphism, of interfaces, and all the other stuff. And another bad thing is that, well, the runtime, since the runtime provides services to the applications, it provides a single control point for all of the application. And it also has a large attack surface, since many of the virtual machines are pre-installed on operating systems today. Think about Microsoft that provides the .NET CLR on almost all of the machines. All of the new machines, all of the new operating system today has the .NET CLR pre-installed. The good news is that, well, an MCR, since it is not a kernel level rootkit, it's an application level rootkit, it leaves traces, right? Since it leaves traces, we have the traditional countermeasure to do, so we can do about it. But we can also use some new techniques. For example, if you want to prevent, by the way, we cannot actually prevent it or maybe detect it completely, because think about it, what happens if OS level rootkit hides the presence of managed code rootkit? This is what I call the second level rootkit, right? But still, you can at least prevent it, maybe if it was before that. So First thing that you can do is do code transformation. Basically, it will not prevent it completely, but it will make the life of the attacker harder. Think about it, what happens if, for example, we're talking about the second one, randomized libraries, which is something which is equivalent to ASLR. What happens if for every runtime, it will contain a different code? So the same DLL, for example, that I created using Reformer will be relevant only to one specific platform. Of course, the attacker can engineer a specific class for the specific machine, but it will be harder, pretty much harder for him. And we have the detection techniques such as the Windows file protection, some kind of watchdog such as tripwire, TPM for checking signatures, and of course the response for these kinds of problem, if we detect it, is to reinstall the runtime itself. Well, the good news is that we can use this kind of technique to do something good. Well, one of the good things is that you can do with this is to create your own runtime and to harden the runtime. We're using the same methodologies that antivirus is using. Well, antiviruses, they're using rootkit-like technique to protect against rootkit, right? We can do something pretty much close to that. We can deploy protection code inside the runtime. Of course, if someone changes the runtime, we can remove it, right? But until it happens, we have protection for the application. And of course, Reformer can be the tool that implements this kind of thing. So we can actually, so we can actually restrict some kind of dangerous operations. Developers will always do mistakes, right? And even though we tell them millions of times, do not use dynamic commands, right? In order to prevent SQL injection. Do use HTML encoding. They will always make a mistake. But what happens, for example, if we remove the ability to do a dynamic SQL query from the beginning? So we can actually harden runtimes. By that, we change their behavior. So, for example, we'll disable the ability to do a dynamic SQL injection. We'll do an automatic HTML encoding for some inputs that we know for sure that we can do. And the next one is interesting. We can make, for example, a .NET application look like a Java application. What happens if I'm going, for example, to the cookie and change it to look like a JSession cookie? I'm confusing, I'm doing the same like against banner grabbing for web platforms. I can confuse the other side. So I'm confusing information gathering steps, and there are lots of other examples. So that the idea is that if I'm hardening the runtime, I'm actually having a better runtime if I'm comparing it to the generic runtime that the vendor provided me. Because it's generic and it's supposed to support all kinds of applications. Well, we are just about in time. So what I'm going to do now is going to do a summary, but we have a couple of minutes, so later on we can ask questions. So we've seen now at this presentation, we've seen that the malware itself can be hidden inside the runtime as an alternate malware playground. So that this is not kernel-level rootkits and device-level rootkits and BIOS-level rootkits. We're also having now application-level rootkits, virtual machine-level rootkits. This is something you should be aware of. Each runtime has its own steps, is its own technique. The concept stays the same. The concept stayed the same, and the basic idea is that you need to know and need to investigate how to change a specific runtime, so that today I exposed the method of changing 3 runtimes, but the concept stayed the same, so we can extend it to other kinds of platforms. Another thing is that code reviews, forensics, basically everything that relates to security, you should start looking for runtimes. Do not take the runtime for granted. People can mess with the runtime. Developers that know that their code might be audited. Think about a rogue developer that wants to hide some piece of code that says, if the account number equals mine, give me more money that I should, right? Developer backdoors. Well, the developer knows that his code might be audited. So he will not hide the backdoor inside the application level code, it will hide it inside the runtime code, right? Framework that we saw allows us to do some kinds of runtime manipulations. Well, with framework, besides of doing MCR-like changes, it can actually do some things that we want. We can actually change and take the runtime to any direction that we want. Let's say you decide to have the color green when someone calls the color blue. Just go for it. You can change the runtime and do that. So it actually lets you to change the reality for the applications. And of course, all of the techniques that I showed you today, well, they can be used by us, the good guys, to create better runtimes and to create applications which are more secure than what they used to be. So if you have any questions, guys, we have a couple of minutes, so I'll be happy to answer. Any questions? Yeah.
Have you been working like with any of the like those VM vendors like .NET or JVM to kind of like talk about like the randomization or things like that?
Well, I contacted them. Well, the answer, the best answer that I got, it was from Microsoft. Okay, and Microsoft, well, they investigated it and they got to the decision, but the decision was it was obvious, is that you need administrator level privileges. Of course, you need administrator level privileges, but I think that virtual machine vendors should raise the bar a little bit. Even though you cannot completely protect against these kind of things, you should always make the life of the attacker harder. And when I'm talking about it, I'm comparing the same thing that Microsoft did with kernel level, with kernel patch protection. Well, kernel patch protection, which is something good. If you're thinking about it, well, if someone has administrator level privileges, he can disable it, but still they did that, because it makes the life of the attacker harder. So this is a good thing to do. I'm going to describe the randomized libraries in the book, so I'm pretty much working on it, and I hope it will be something that will be useful by the application vendors.
Are you aware of any real-world attacks that have taken place that use this kind of rootkit methodology?
No, but I'm sure that I had many bad guys out there that says, well, someone knows about what I'm doing now. I'm stopping doing it.
I'm questioning when, per se.
Yeah.
I can see it happening.
No, I didn't see it on the wild, if this is what you're asking. Other questions, guys? So, well, thank you very much.